Hello, thank you for watching this video. So in this video we're doing question 6 of November 2021, question paper Physical Sciences paper 1. And this is the Doppler effect. So I'll read question 6 statement and then proceed to answer the questions that follow. So let's go. They're saying the siren of a stationary ambulance emits sound waves at a constant frequency of 680 Hz. A man standing with a detector records the wavelengths of sound waves emitted by the siren as shown in the diagram below. Let me read this thing again. The siren of a stationary ambulance emits sound waves at a constant frequency of 680 Hz. A man standing with a detector records the wavelengths of sound emitted by the siren as shown in the diagram below. So I've tried to draw this equation. So you have this ambulance, which is the source of sound, stationary. And then you have that detector here, there, or this detector, which is the observer, or you can say the listener in simple terms. So this ambulance is emitting sound waves, right? Emitting sound waves at a frequency of 680 Hz. This is the frequency of the source. And then this friend of ours have a detector there, and that detector measures the wavelength of waves of sound emitted by the siren. So that detector of ours is measuring the wavelength of sound emitted by the siren. No problem. This is straightforward. Then they went on to say the speed of sound in air is 340 meters per second. So you are also told that the speed of sound in air is 340 meters per second. No problem. So we go to 6.1. So 6.1, calculate the wavelength of the detected sound. So they want us to find the wavelength of the detected sound. So what are we given? We are given that the frequency of the source is equal to 680 Hz, right? And also given the speed of sound in air to be 340 meters per second. So what do we want? We want the wavelength. We know that the speed of sound is equal to the frequency times the wavelength, right? Which implies that, actually we can just substitute. So we have the speed of sound, which is 340, is equal to the frequency. What is your frequency? It's 680 times the wavelength, which is what you're looking for, right? Then divide by 680, divide by 680. So you get that your wavelength is equal to the answer of whatever that you will get here, which looks like 0.5 meters. And I'll just double check. 340 divided by 680. Yeah, it's 0.5 meters. So that is your wavelength. Okay, so now we continue to 6.2. We're given another statement, so let's go. They are saying the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of sound, which differs from previous reading by 0.05 meters. I'll read this thing again. They are saying the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of sound, which differs from previous reading by 0.05 meters. So they are saying now the ambulance now is now approaching the man at a constant speed, right? So our ambulance is now approaching our friend with his detector there at a constant speed, no problem. They are saying now what happens is as the ambulance is approaching our friend, the wavelength changed. That's what they told us. So which means the wavelength of the detected wave sound changed, right? No problem. So let's read the statement. And it changed, or it differed by 0.05 meters. So we go to 6.2. They are saying state the Doppler effect. So what is the Doppler effect? That's what they want you to state. So I normally define Doppler effect as the observed change in frequency of a sound due to the relative motion between the source of sound and the observer, right? or you say it is the observed change in frequency of the sound, right, due to non-zero velocity difference between the source of sound and the observer. Because if you have a non-zero difference between the velocities, which is now you have a non-zero relative velocity, then now you observe Doppler effect. But now, if the relative velocity is zero, which is there's no relative motion between the source of sound and the observer, then you won't observe the Doppler effect. So let's write it down. So I'll say the Doppler effect is the observed change in frequency of a sound, right, due to the non-zero velocity difference, which is what they called relative velocity. Between the source of sound and the observer. So, we're saying Doppler effect, it is the observed change in frequency of a sound due to the non-zero velocity difference between the source of sound and the observer. That's how I like defining it. Then we move to 6.3. What are they saying at 6.3? 6.3. How would each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? Choose from increased, decreased, or no change. So they're asking now some questions here, and they wanted to compare these questions to the previous ones when the ambulance was stationary, right? Let me read this thing again. How each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? Choose from increased, decreased, or no change. So 6.3.1. They're asking the distance between wavefronts, right? So when your ambulance is stationary, right? Let's say this is your ambulance here. Let me try it here. Let's say this is your ambulance here. Let's say your ambulance is stationary. So, which is the velocity of a source is 0 meters per second. So, when the ambulance is stationary, the wavefronts are equally spaced out. You can see? I'm trying to make these distances here between the wavefronts equal. Not so equal down here. So, when the source of sound is stationary, the distance between the wavefronts is equal. It's equal, right? But then now, this was the first situation which we were given. This was the original situation, right? Then now, on the second situation, the ambulance now is moving, right? Our ambulance is moving. So here's our ambulance. It's moving to that side. So it has a velocity now, right? Or it has speed, it is moving. So now, when the ambulance is moving, and behind the ambulance, the wavefronts are spread out, and in front of the ambulance, they are closer together. You see the distance. You see it there. So behind the ambulance, the wavefronts will be spaced out. In front, they'll be closer together, right? So, if you are in the front here, because of these wavefronts will be getting it, because many waves will be hitting you per second, you'll observe high frequency. Because if you're standing here in this position, you'll be reached by many waves per second because they are getting to you at a higher rate, right? So you will be hit, or your detector will be measuring or will be detecting many waves per second, right? So you'll observe higher frequency. But if you're at the back here, you'll be hit by this one, then after some time this one, then after some time this one. As a result, fewer wavelengths will be reaching you per second, or fewer wavefronts will be reaching you per second. As a result, you'll observe a lower frequency. That's what happens. So, in our case, the ambulance was moving towards the source of sound. Sorry, the ambulance was moving towards the observer, right? Because our ambulance is the source of sound. So it was moving towards the observer. So now the wavefronts in front of the ambulance will be decreased. They will be smaller. So the distance between the wavefronts will be smaller. So from this case, we will say, we'll just choose decreased here. Go to the next one, 6.3.2. What are they saying? They are saying the frequency of the detected waves. I've already answered that. Because you can see the ambulance is moving towards our source of sound, right? So if it's moving, our ambulance is moving towards the detector, not the source of sound. So you can see that if the ambulance is moving towards the detector, the wavefronts are closer, which is the wavefronts are closer together. So this detector of ours, which is sitting there with our man, it will detect more waves per second, right? As a result, which means higher frequency. The greater the number of waves that are detected per second, the higher the frequency, right? So we will say the frequency will be increased. Done. Then we move to the next one, which is 6.4. What are they saying at 6.4? They are saying now, calculate the speed of the ambulance. They want us to calculate the speed of the ambulance. So we know that the frequency of the listener is equal to velocity of speed of sound in air plus or minus velocity of a listener all over speed of sound in air plus or minus velocity of a source times the frequency of the source. Right? But then we have to decide if we're going to use plus or minus at the top or plus or minus at the bottom. So, because our ambulance is approaching our detector, right? As a result, we will observe what? Higher frequency. So this ambulance approach will result in what? In higher frequency. It will result in higher frequency, which means there will be higher frequency of a listener, which is our detector in this case, right? So if we want, in this formula, if we want to observe the highest possible frequency, which means the denominator should be, if in this formula here, if we want to observe the highest possible frequency, right, the numerator should be as big as possible and the denominator should be as small as possible. So, because this is multiplying the top, right? So if your frequency of source is multiplying the top, you want the top to be as big as possible. So at the top we should have a plus, and at the bottom we should have a minus. So this plus will make the numerator as big as possible, and this minus will make the denominator as small as possible. So if this ambulance was moving away, the signs would be the other way around. So now what do? We have the frequency of a listener. Do we have it? Oh, actually, wait. We have the speed of sound in air to be 340 meters per second, right? What else do we have? We have the frequency of the source to be 680 meters per second, right? What else? Do we have the frequency of a listener? No, we don't have the frequency of a listener. But we do have the wavelength detected, which is the wavelength of a listener. Right? The wavelength that was detected initially. You initially detected 0.5 meters of wavelength. Right? It was the initial wavelength that was detected when the ambulance was stationary. And then the ambulance, then it started approaching, right? And the wavelength changed by 0.05 meters. So this 0.5 meters is the wavelength that was observed when the ambulance was stationary, right? And then our ambulance started moving, and then there was a change in this wavelength by 0.05 because they said the detector now, they said the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of a sound which differs from the previous reading by 0.05, which means the new wavelength of a listener will differ from this one by 0.05. So by saying differ by 0.05 is either to get the new wavelength of the observed wavelength, you either add 0.05 or subtract 0.05. But what do? Do we subtract or do we add? So there's something that we have to consider. We said the speed of sound in air is equal to frequency times the wavelength, right? And if you want your frequency, which is what we want, your frequency is equal to speed of sound in air divided by the wavelength. So from this, you can see that the frequency is inversely proportional to your wavelength, right? They're inversely proportional. What does that mean? It means that if inversely proportional, what does that mean? Inversely proportional in this case. It means that if you increase your frequency, right, it will result in your wavelength to decrease at a similar proportion. That's what that means. So it means that if you increase your frequency, your wavelength decreases in a similar proportion, or if your frequency decreases, then your wavelength will go up in a similar proportion. That's what this inversely proportionality means. So in our case, we said that if the ambulance approaches the guy, we'll observe a higher frequency. If our ambulance is approaching this guy and the detector, we'll observe a higher frequency. Which means that if we observe a higher frequency, that means the wavelength have to decrease. Since our ambulance is approaching our guy and we observe a higher frequency, because the frequency is inversely proportional to the wavelength, we know that the wavelength have to decrease. Which means in this situation, we have this case here, where the frequency of the observed sound is increasing and the wavelength is decreasing. Which means Now we know that our wavelength will decrease by 0.05 because the frequency went up, so the wavelength have to go down because they are inversely proportional. So in that case, our wavelength is equal to 0.5 minus 0.05. So the wavelength of our listener now is equal to the answer to this thing here. So what do we say? We say 0.5 minus 0.05. So the new wavelength is equal to 0.0 or 0.45 meters. That is the new wavelength of the observed frequency when the ambulance is moving towards our friend. We'll observe this wavelength. Right? No problem. So, as you can see, this wavelength is smaller. The reason it is smaller is because the frequency went up after the ambulance started approaching, which is the wavelength had to go down. Okay. But now we don't want the wavelength of a listener. What we want is the frequency of a listener. So, what do we do? It's okay. The frequency of a listener, or we say that the frequency is equal to speed of sound divided by the wavelength, which is equal to 340 divided by 0.0 or 0.45. So the answer to this will give us the frequency of a listener. So 340 divided by 0.45, which comes out as 77 or 755. 755.56 hertz. So this is the frequency of the observed sound. It's that one. And it's higher than that of the source of the sound because this detector is detecting many sound waves per second. So that results in higher frequency. That's why we have that high frequency there. Then, in this case, we have everything now because this is the frequency of our listener. If you go to our formula, we have the frequency of a listener, we have the speed of sound in air, we have velocity of a listener, which is the source, which was stationary. This is the velocity of a speed of sound in air. We want the speed of the ambulance because we have the frequency of the source. We just substitute from there. So, substitute on this formula here. What do you do? What is the frequency of a listener? Here is it. It's 755.56. Is equal to 340 plus velocity of a listener, which is what? Stationary. Especially, so the velocity of a listener called 0 meters per second. I had it written there. So is 0 meters per second over 340 minus velocity of a source, which is what we're looking for, times the frequency of a source, which was 680 hertz. Then we're solving for this. What do we do? Cross multiply. It's okay. This times this, so we have 755.56 times 340 minus Vs is equal to 340 times 680. Right? Then we continue. So we have divide this side by 755.56 divided by 755.56. So this and this go away. So I will have to clean a board somewhere. Let me clean this board. I'll clean just this side. Okay, so now we continue. So we said, so this side will be left with 340 minus velocity of a source, because these two did cancel out. Then is equal to punch the answer of this thing. So you said 340 times 680 divided by 755.56. So you get that this is 306.00. So we transpose this to the side so that it becomes positive. So you have 340 and transpose this one to the other side. 340 minus 306 is equal to velocity of the source. Therefore, your velocity of the source is equal to the answer to this. So 340 minus 306. So the velocity of the source is 34 meters per second. Actually, they wanted the speed. This is the speed of the ambulance. And we're done. I hope it does make sense to you, as it does to me. If you have any questions, you can just let me know in the comment section. Otherwise, thank you for watching. Cheers.